Right, the third and final part of our discrete random variable chapter, binomial distribution. This is fun. It's got some applications that you can use to calculate probabilities of different things in everyday life, and it's fairly straightforward, but we need to make sure we know what we're talking about. So, a binomial experiment. Bi is an indication that it's going to involve two, isn't it? Two outcomes. Binomial experiment, there are a fixed number of independent trials, so I'm going to do something and I'm going to repeat it over and over again. There are only two possible results, two outcomes. We classify one of them as a success and one of them as a failure. It doesn't have to be really a success is a positive thing and a failure is a negative thing. It's just one that we're looking at and one that we're not looking at. One that we're counting and one that we're not counting. The one we're counting, the one we're interested in, that's what we call a success. The probability of that success, of that outcome that we're interested in looking at, the probability of that outcome happening is the same from one trial to the next. It's assumed for these binomial distributions that that is the case. If that's not the case, we can't use these rules. But pretty much we're going to be able to. So they had a little picture of a spinner up here. They're going to spin it. It's going to land on one of those flat edges each time. Assuming that there's no bias in the spinner, 3/4 of the time it's going to land on a blue one. 1/4 of the time it's going to land on a white one. This is an example where I might be interested in counting how many blues. I might be interested in counting how many whites, whether I describe the success as a white or a blue. Depends on what I'm looking at. So in this particular example, they're going to say a success is a blue result. And they're going to do this 3 times. They're going to spin the spinner 3 times. So for 3 times, we can just fit in a tree diagram with 2 outcomes with the probability written along each line of each branch of the tree there. And we know how to work out those probabilities. We've been doing that since grade 9, possibly even earlier for some of you. The first one you can see, it's going to be 3/4 times 3/4 times 3/4. They've just written it there. They haven't bothered to figure it out because this is going to be really important. That outcome occurs once. Blue, blue, white, 2 blues and a white, actually occurs 3 times. I've used their little coloured highlighting there to help you see that. In each case, the probability, the first one, 3/4, 3/4, 1/4, 3/4, 1/4, 3/4 was the next combination, and then 1/4, 3/4, 3/4 would be the third combination, the probabilities being multiplied together. Each of those is going to actually multiply to the same thing, isn't it? What's it going to be? 3 3s and 9 over 64, so it's going to be 9 over 64 for each of those particular outcomes. So the probability of getting 2 blue and 1 white, regardless of what order it happens in, would be 9 over 64 plus 9 over 64 plus 9 over 64, 27 over 64. Which is easy enough to go ahead and calculate. All right, if we go a little bit further down, so we can do that for each of those outcomes. So here the probability of getting 0 blue results, 0 blues from 3 spins would be white followed by a white followed by a white. That's 1 over 4 cubed, 1 over 64. We can see you follow the same procedure for the others there, and you can write your distribution, and there is what the distribution would actually look like. Very interesting. What we notice is, we saw up here how this triple B occurred once, 2 blues and a white occurred 3 times, 2 whites and 1 blue occurred 3 times, and 3 whites occurred once. This is exactly the same as the coefficients we get when expanding a binomial product. When we expand a plus b to the power of 3, we're going to get 1a cubed plus 3a squared b plus 3ab squared plus b cubed, 1b cubed. So Pascal's triangle coefficients correspond to the number of different ways these things can have. You might recall they are combinations, and that was way back in chapter 7. I'm sure you do. Isn't it terrible how they've used these ugly decimals rather than writing nice fractions? But that's okay. Is this a probability mass function? Yes, if I add up each of those probabilities, the total is going to equal 1. I really wish they had done it in fractions so you could see it there. But that's okay. The sum of the probabilities, oh, there you go, they've done it there. They've added them together as 1. Interestingly, this is the binomial expansion. That's what I was talking about before, those coefficients from Pascal's triangle. 1/4 to the power of 3, that happened once. 2 whites and a blue happens 3 times. 1 white and 2 blue happens 3 times, and 3 blues only happens once. The 1, 3, 3, 1, it's just a binomial expansion of 1/4 plus 3/4. We know if we were actually to calculate that, 1/4 plus 3/4 is 1, 4/4, and when I raise 1 to the power of 3, I'm left with 1. So in general, in a binomial random variable with n trials and a probability of p successes, and we write this down here, x is distributed in a binomial fashion. So x is distributed binomially with n being the number of trials and p being the probability. In this case, we would have had x is distributed as b bracket 3, because we were doing 3 trials, and we were counting blue ones, so p would have been 3/4. And then that would be the binomial distribution. In this example, they're getting you to expand 9/10 plus 1/10 to the power of 5, so we can get our values out of Pascal's triangle. It's going to be 1, and the next one was 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And then adding up, remember to get each one, it starts with a 1, and I go 1 plus 4, that's going to give me a 5. 4 plus 6 is going to give me a 10. 4 plus 6 is going to give me a 10. Then I've got another 5, and I've got another 1. It's probably helpful if I put spaces in between each of those so you can see it more clearly. But you're getting the idea there. Unfortunately, while I'm teaching on this computer, it makes it easier for me to do a lot of things, but the writing on the tablet is less easy to do in my current setup. I'll try and improve that for future videos, but for now, you can just persevere. You can see how this is going to be. Very much Pascal's triangle. I know you've seen the rest of it written out before. I don't need to go through all of that again for you. So we could expand that and we could write each of the different things. Here we're talking about an archer has a 90% chance of hitting a target with each arrow. If 5 arrows are fired, determine the chance of hitting the target twice only. This is effectively saying find the probability that x equals 2, the number of successes is 2. So here we're saying find the probability the number of successes is 2. Which of the bits in the expansion corresponds to hitting the target exactly twice? Well, 9/10, 90% is the chance of hitting the target. So I'm going to need the one with 9/10 to the power of 2. And you can see the coefficient from my Pascal's triangle from my 1, 5, 10, 10, 5, 1. The coefficient when I have 2 successes and 3 failures is 10. So to work out this probability, I take 10, multiply it by the 9/10 to the power of 2, and the other 3 results must have been 1/10 to the power of 3. And that adds up to 0.0081. So the chance of someone who's got a 90% chance of hitting a target, the chance that they only hit the target twice in 5 shots is very small indeed, 0.0081. The 10, that's the number of different orders in which they could have hit or missed the target. They could have hit the first 2, missed the next 3, could have gone hit, miss, etc. All the way down to miss, 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 hit, hit. How many combinations are there? There are 10. That's what that 10 is telling us. The probability they hit the target at most 3 times, so there's a couple of ways you could do this one. If we were doing it without the calculator, first way would be to find the probability they don't hit it at all. They hit it once, they hit it twice, they hit it 3 times. Alternatively, I could take the total probability 1 and subtract the probability that they hit it 5 times or 4 times. Here they've decided to add them together. If you did it in the other way, if you just did 1 minus this little bit here, and then 9/10 to the power of 5, 1 minus those last 2 terms, that would also give you 0.0815. Using technology to find binomial probabilities, I've got the calculator instructions there as well. Easy enough to do, the TI is over there as well. So you go to Stats, you choose Distribution, Binomial. When you're looking for just one value, BPD, I think of the people who have trouble saying specific and they say Pacific instead, one specific value. It's a specific value, but this is a binomial probability distribution, so it's finding an individual probability. You can just do it straight away on your calculator. The data is a variable. I wanted 2, the number of trials were 10, the probability of a success was 0.3, and there would be my result. That's obviously not matching up to the example we just did, which was different, but you get the idea. Because we don't have 0.3 up there. S, a binomial cumulative distribution, so the second part of that question where I wanted to know up to 3 successes. In this case, they're doing an example where they want to know up to and including 5 successes from 10 trials with a probability of 0.3. You can put binomial CD, you put in your lower limit and your upper limit. So I want between 0 and 5 inclusive. I'm doing 10 trials, probability of success is 0.3, and it spits out the answer there. So binomial distribution, binomial probabilities. Really easy. Once you do a couple, you'll get the hang of it. NCR, P to the power of R, Q to the power of N minus R, where Q is 1 minus a probability. I might write that out. We'll go through that in class, but that's just an easy way for you to remember what you have to do there. And we've got the probability function and the cumulative probability function. Little example just to follow through here. 72% of union members are in favour of a change to their conditions of employment. So they took a vote. 72% are going to vote yes. A sample of 5 members is taken at random. Find the probability that 3 of those members are in favour of the change in conditions. So I'm after one specific value. So it's going to be binomial PD if you're using a calculator. Or if I'm going to do it without the calculator, what am I going to do? I'm going to do over here, this is that NCR P to the power of R, Q to the power of N minus R that I was talking about. I want to know the chance of getting 3 successes. So from the 5 trials, I want to know how many different combinations there are that include 3 successes. Because I want the success to happen 3 times, that's got a probability of 0.72. I raise that to the power of 3. The chance of a failure in this situation is 0.28, 1 minus the 0.72. So it's 0.28, and I square that because the total number of outcomes has to equal the number of trials, 5. So if I knew that this one had to be 3, then 5 minus 3 gave me 2. And I multiply those together, and that's where I get my 0.293 for exactly 3 out of the 5. Probability that at least 3 out of the 5 are in favour, I would have to do it for 3, and then I could do the same calculation with 5C4, 0.72 to the power of 4 times 0.28, and 5C5, 0.72 to the power of 5. I wouldn't need the 0.28 to the power of 0 because that's going to be 1, and I could add them together. So I could find the outcomes for 3, for 4, and for 5, and add them together. Or alternatively, I can just use the cumulative distribution on my calculator. Up to and including 3 members was 0.862. We want to know, oh, that's, okay, they've done it slightly differently there. They've just spat out the answer. They didn't show you the working behind it. Maybe I should get my calculator out and let's just do it with our calculator. I can bring it in over here. So let's do the example. I want statistics, number 2. Exit out of where we're doing our last thing. We're interested in a distribution. It's a binomial distribution, and it's BCD because this is going to be a cumulative distribution. Now, I don't want that to be in a list. I want it to be a variable, so I change it to variable. My lower limit, there's 2 ways you could do this. Here they want x to be greater than or equal to 3, so the smallest value is 3. The upper limit is 5 because that's how many trials we're doing, how many people we have. The number in our sample was 5. The probability of a success in any individual one was 0.72. And I can go ahead and calculate that value, and it comes out nicely. If you've got the TI, usually what happens is it does... Oh, why did that disappear there? Well, I don't know why it disappeared, but I managed to get it back eventually. With the TI, when you're doing binomial CD, it's counting up to and including a certain number of successes. So here we've got 5 trials. They've done, I don't even think that should be a 0 there. It should be saying up to 3 successes or up to 2 successes. Oh, no, okay, this is what it is. Binomial CD, so the number of trials is 5. The probability of a success in every trial is 0.72. Here they've said up to and including 2 successes. And then what you do is you go 1 minus that, and that will tell you 3 or more successes. I could achieve that on my Casio the same way. So had I gone back up here, let's just go back up and edit. I want my lower limit to be 0, and my upper limit to be, is going to be 2. So that's now finding the probability between 0 and 2. I get the 0.1376, and then if I go 1 minus that, that's where I'm going to get the right answer there. So that's the cumulative distribution. I might as well step through the distribution. Binomial BPD for one, remember, specific value. Hard to forget that now, isn't it? X, we want to know, in this case, we wanted to know 2 successes. Was it, or 3? It's gone out of my head now. I think it was 3. Yeah, 3 successes. 3 successes, 5 trials, probability of 0.72, and we get the correct answer there. So using your calculator, pretty straightforward. To do these calculations, make sure you're writing in your exams this sort of thing. And this, just remember, x tilde b, this is x is distributed binomially, n the number of trials, p the probability of a success. We're going to be dealing with binomial. We're also going to have our normal distribution that we'll look at later for a continuous probability distribution function, and we'll look at that later on. Last couple of things to learn. The mean and standard deviation of a binomial distribution. The mean is just the number of trials multiplied by the probability, and that's it. So if I took 100 people in that, it was going to be a mean of 0.72, wasn't it? Not very surprising there. Mean you take, it's just the expected value. So each score multiplied by its probability. The variance, in this case, the number of trials multiplied by the probability. The variance is n times p times q. Q is the same as 1 minus p. Q, the probability of not a success, probability of a failure, which is always 1 minus the probability of a success. So that's the way they've chosen to write it there. And the standard deviation is the square root of the variance. There's a proof along the side that you do not need. But you can have a look at it, and again, it's useful to read through exactly what's going on there. But let's just do an example to finish us off here and see what we mean by that. A fair die is rolled 12 times. I assume it's a standard 6-sided die. X is the number of 6s that result. Find the mean, variance, and standard deviation. Well, the probability of rolling a 6 is 1 out of 6. So to find the mean, I take 1/6 times 12, because I did it 12 times. Probability times the number of trials. I'm expecting 2 6s on average from my 12 rolls. What about the variance? The variance, I'm going to take 12, the number of trials. Probability of a success was 1/6. Probability of not getting a 6, a failure, is 5/6. Multiply those together. There's my variance. How do I find the standard deviation? I square root that result. Square root of 5 over 3, 5 root 3 over 3, or approximately 1.291. I'll add this video in below the other two. That's it for the chapter. Discrete random variables. Again, fairly straightforward. A little bit of work to do just to get your confidence up, but these are giveaway marks in the exams. A lot of people struggle with them because they just think, oh, I don't need to practice them. Just do a couple, make sure you're really confident. If you've got questions about it, really ask me questions about why it is that we do something. Try and build that understanding, and then you'll be good to go. These will be nice, easy marks for us to score in our exams. Best of luck. I will see you in the next video.